Alrighty, thank you, Jessica. It's Patrick up from the Northland, where it was a little chilly this morning, but that's fine with us. So you'll see on the first slide is it will be interactive. So please join Poll Everywhere via one of those two methods. There'll be a number of times where we're going to ask for your input. And kind of where we're going, obviously, is the proper use and then also the misuse of ensemble deterministic data, kind of helping with the fire hose of data and just kind of taking a look at what humans do best and what machines do best. First, I'm going to start you off, then I'll pass it to Tommy. More of a philosophical start to the presentation, and then we'll get into some more kind of nuts and bolts kind of stuff. But Tommy, if you want to go ahead and advance to the next slide, which is immediately going to be asking for your input. So what is the difference between predictability and uncertainty? So as you submit, you will see everyone's responses pop up. And this text wall, I think, is what Poll Everywhere calls it. So predictability deals with outcomes, uncertainty deals with confidence. One person so far. I know there's more thoughts on that. Let's hear them. You need the link up there right at the top of that slide is the Poll Everywhere link for using the Grand Forks account. We'll just kind of wait. We'll see if what else we get. No knowns, known unknowns. Very, very good. Very good. We'll take just a few more, and then we'll move on to at least some of my own thoughts. Very well. Well, that primed the pump. We'll see what happens the rest of the way here. So Tommy, if you want to advance to the next slide. So obviously there's some type of a difference, and the way we think about things matters. So why predictability? I think it's important to first start out that remember why you're here is that the atmosphere has an inherent intelligibility. There's something to be known about it. Otherwise, why do we show up? Why do we show up to seek to understand it or to predict it? It's because it has inherent intelligibility, that there's something to be known even at day 5, 6, 7, 8, 9, day 30. There's something to be known. And that's why we show up and keep clicking away there, Tommy. So you really can't name a range or phenomena that we can't say at least something about. You may not be able to say fully, but there's at any time range, there's always something to be known. Even if the predictability is low, that is something to be known. And so we're trying to, kind of shape the way we think, that predictability allows us to have the right set of expectations and know what questions we're trying to answer. So that kind of sets up the framework that we set out to know something because the atmosphere is intelligible. That's why the science has developed. And that's why we're showing up, is that even at whatever the time range, there's something to be known. Keep going, Tommy. I think it shifts our focus from what we don't know. I think we throw uncertainty around a lot, almost too much. We just slap uncertainty on there and we're good. Well, I think that puts us to what we don't know. And whereas predictability, at least that kind of mindset, puts us more into what we do know, which is often more than we give ourselves credit for. So keep rolling there, Tommy. So knowing 2 or 3 or 4 bins of scenarios means you know a lot, right? WPC cluster page, break it apart into 4 scenarios. Of course, that's only 4, and it's only using the 500 millibar pattern. But boy, there's something to be known, even if there's 2 different model camps or things like that. I think if we focus on uncertainty, we're largely pinning ourselves to the deterministic answer, which obviously we get to. Obviously, we need to land the forecast at some point, stealing words from Greg Mann. We need to get the wheels on the ground, but focusing on that uncertainty, I think, puts us too much into the deterministic answer. We're too much pinned to one certain grid that's staring us in the face with the GFE. And the last bullet point shouldn't be popping up there. And that's just to reemphasize that we often know a lot more than we think that we do, or give ourselves credit that we do, and at longer time ranges. And keep clicking there, Tommy. Yeah, day 5. It's all about, I think, trying to say what we know when we know it. So even at, say, day 5, yeah, you have no idea what exactly is going to happen. 100%, I agree with you there. So, but you know a handful of scenarios. So there's a lot you can know. There's a lot you can share, even without knowing the one answer. So predictability kind of really sets us up for focusing on what we know and saying what we know when we know it. And that might stretch us a little bit beyond some of our legacy ways of thinking, but that's okay. So, all right. So how does all this fit into the modernized forecast process? Kind of the key thing out of all this slide of a lot of words is what's highlighted in the red box, which is to focus on things that humans do well. Before we go to the next slide, I'm going to ask you what you think humans do well. So kind of get those thoughts going and ready for when we get into the poll everywhere question next. But out of all this, obviously we're trying to leverage probabilistic information, but especially we're trying to also, shift our mindsets to what is it that we do well, and using that in concert with what humans do well. So Tommy, if you want to go to the next slide, and what do humans do well, especially in the context of forecast operations, which is also largely related to just human nature and what makes us human. But what do we do well compared to a machine? Pattern recognition. What else do we? What do we do well? What defines a human compared to a machine? I like it. Communicate. We message. Provide the context. Obviously, that's something a machine just spits out data. Communicate. We can overthink. I like that one. That's a pitfall of being a human, is that we can think, but then we can overthink or we can underthink, and that's just being. Alrighty. Obviously, again, there's a chat room that's available that we can keep that going. But obviously, a lot there on providing context and really thinking about machines are just providing data, and that's all they're doing. And we can go beyond that. So Tommy, let's throw some stuff up there. So the reason why you're sitting in your forecast office right now is because you have an ability to reason and to judge, and you make present what is to be known. That's why you're here, and that's why humans do. What makes you a human? You can reason, and you provide judgment. There's a speaker back at NWA a couple of years ago, and great analogy about radiologists. Now, machine learning is going to replace all radiologists because the machine can just scan a bunch of images and tell you what's wrong or notice something. And so what they noticed, though, is I'm pretty sure there's still a lot of radiologists around, and there's actually more need for them because it's just more efficient, because let the machine do what the machine does well, but you still need the radiologist to provide the judgment of what to do. So this predictability, especially assessing predictability, necessitates judgment, and that's what you do as a human. And there's, I think, 1 or 2 more bullets on there, Tommy. Partners are coming to you for your judgment that informs the predictability of what they need to know. They're not coming to you for what you don't know or for the unknowns, the uncertainty. They're coming to you for what is to be known, which is 2, 3, 4 scenarios. Machines can kind of help quantify, why there may be low predictability, but obviously we're providing the context for why that predictability exists. So your reason, your judgment is why you sit where you sit in the offices. All right, Tommy, next slide. All right, so now kind of based on that more philosophical approach, how do we kind of start to, shift this towards what we do and why we do what we do? And where does assessing predictability fit in this modernized forecast process? So what's highlighted there is targets of opportunity, which has been talked about for a long time, and is at times very inconsistently applied. There's been many attempts at definitions, but unpacking targets of opportunity deals with predictability. We're going to try to do that. So if you want to advance to the next slide there, Tommy. When you hear target of opportunity, what do you think? And I'm looking forward to see what, because it's a phrase that we used a lot, and again, it's inconsistently applied. Short term, certainly in the short term, there can be a target of opportunity. Adding value. Improving upon the NWP. Recognition of bias, right? Yeah, so I'm seeing a lot of things that get to trying to improve upon things, right? Which is fair. And I think it goes beyond just improvement. It's adding value. So this is a very kind of busy slide, so I apologize for that. But this assessment of predictability is really at the foundation of what we're going to bring out and what we're going to do. And so I think actually if we go to the next slide, Tommy, it would probably be a little bit more clear. So this target of opportunity and predictability assessment. So how do we leverage or understand predictability? Well, we have two camps that need to be married together. And amazingly, that's half the title of this presentation is marrying probabilistic and deterministic data. That we're using the power of deterministic models to help us apply our conceptual models, while also allowing the probabilistic guidance to build out more so that spectrum of solutions, and especially that the foundational patterns, which are what we do best, helps to give us that sense of predictability of what does northwest flow give me for predictability or typical patterns? What does southwest flow? Zonal, I mean, just keeping it simple like that. And then relating that to the impacts, and then targets of opportunity, which is where your ability to reason and judgment make an impact. So next slide, Tom. So that's how they're two connected. So, a couple things here is, how much predictability do you need to be able to say what you know when you know it, versus how much predictability do you need for it to make a grid edit? And they're not the same, right? Why not send out a DSS packet day 5 or 6 talking about a winter storm that's already being talked about in the media, right? You are going to have low predictability, right? But you're able to talk about that low predictability compared to actually trying to manipulate a grid. So just because there's low predictability doesn't mean that you can't do something. And so that assessment of that helps to really provide the context for what we do, and that understanding of maybe how much we're going to have to message in regards to scenarios and how much more context we may have to apply, especially in low predictability scenarios. But that's why you're there, is to provide the context. And so low predictability doesn't necessarily mean you don't do anything, right? It may mean you may not touch the grid, because the grid just needs to be in the ballpark. But the predictability, or kind of taking that, saying what you know when you know it, means, well, there are some open seats in this section, and this section, and this section of the ballpark. And that's kind of the framework that we're going for. So, all right, let's try to surface from some of the steeper philosophical stuff here, Tommy. Keep rolling it through. So what we're really trying to do is to adjust the way we think, because that's the only way we change the way we behave, is by changing the way we think. And a lot of us trained in school and professionally to meet the deadlines and get through the process to determine a most likely outcome, right? And that's just the nature of having deadlines and trying to get through things, the nature of some of the software that we have, which has a whole lot of deterministic grids facing you that you need to touch. But we need to try to change the way we think, and not just trying to understand what's the most likely outcome at each location, but is predictability high enough to message only the most likely outcome at each location, which means that sometimes the grids are going to have to be put on somewhat in their own context of, if it's in the ballpark, fine, because you have one grid. You can't message 4 different things with one grid, right? So, trying to change our mindset that we're not only just trying to message the most likely outcome, but is the predictability high enough? Is that going to be the only thing we want to message? Next slide, Tommy. So, asking ourselves questions, right? What's the most probable outcome? What are the reasonable alternatives? And what are the probability of an extreme outcome? And next slide, Tommy. So part of it is just asking us these questions, which are founded in these pillars of predictability and assessment, which you're going to see play out through a lot more of this presentation. There is a preferred order to them, although it's not overly important. Everyone takes in data differently. But what we're trying to instill is these 3 pillars, is understanding the pattern and establishing the predictability. So what are my large scale patterns? What kind of conceptual models are there? Have I met a predictability horizon? And Tommy's going to touch on all this stuff. From that, how extreme is this? What are the extremes of the scenarios? Well, there's a lot of tools that help you assess that. R climates, N climates, machine learning, all that kind of stuff, EFI. And then, really tying these probabilistic patterns and trends to deterministic conceptual models. The GFS on its own is still the best way to, assess a conceptual model for heavy banded snow, or for some type of Maddox pattern for a heavy rainfall event. But kind of these elements in the predictability process is kind of going to be the really drive the rest of this presentation. Really is these 3 pillars of how we're going to approach this. And there's a preferred way, going from top to bottom here and understanding the pattern. And from what that pattern is, we can have an understanding of how predictable it is or isn't, and which is going to still drive what we do, but there's still something to do even if the predictability is low. Then establishing, well, how extreme is this event? And then all this ties back to key conceptual models, which are still very much applied using deterministic guidance to be able to apply those conceptual models. So with that, I'm going to pass it off to Tommy, who's then after that going to pass it off to Andy, and we'll take you through more of a practical application of all this.
Yes, thank you, Patrick. Just one thing I want to mention before we kind of go into some of the details within the elements in the predictability assessment process is that we're just kind of 3 crazy Sues here with ideas that we're passing along. None of this is really set in stone. We'd love to hear your thoughts, your ideas, what you agree with, what you don't agree with within that Google Meet chat room. That's kind of what that chat room is set up for, is to have a discussion about this. As we move forward to trying to adjust our mindset to thinking more probabilistically, I think it's really, really important to have a discussion, right? To ensure that we're all on the same page, to talk through our concerns, our issues, how we do things. And the important part is that we do all these elements so that we're kind of on the same page, so that we're going through the same process. But like Patrick said, I'm going to go through some of the elements and specifics, and just go through some examples and why some of these elements are important, and how to use some of these elements. The first thing we have up is the predictability horizon. And I think if we're going to change our mindset to thinking more probabilistically, we always have to have this concept of the predictability horizon in the back of our heads, and we have to think about it, and we really have to not just unconsciously think about it, but really bring it up in our conscious mind often if we're going to think about predictability and that sort of thing. So, the horizon of predictability is the point after which a dynamical system becomes unpredictable given initial conditions. I really like the alternate definition, that being inside the horizon of predictability is when predictability is high enough to act on a perceived threat. And not all events, all events might have different impacts. And even in the same event, the details are going to be different. Each detail, each element, each hazard impact may have a different predictability horizon. Think about a large Colorado low type system. Wind may carry a longer predictability horizon, but the amount of snow or where the heaviest snow happens may carry a shorter predictability horizon. And I just have two examples here of a Colorado low versus a banded snowfall event. And if you're thinking about this in terms of predictability horizon, obviously the Colorado low is more of a synoptic force type system that would carry a longer predictability horizon, where the banded snowfall is more of a mesoscale type force system, smaller scale that would carry typically a shorter predictability horizon, especially with the location of where that banded snow is going to fall. So I think this is our last poll everywhere question, and I'll hide the answers, I believe, just for a little bit. But which of these do you feel would carry the shortest predictability horizon? And really the point of this question is just to kind of make sure we're all on the same page about what we're talking about when we say predictability horizon. So we have one result in so far. We've averaged about 9 or 10 responses so far. So we'll wait for this to get up to maybe 7 or 8 and then start showing the answers here. So I give this a version kind of this talk at a forecasting class at the University of North Dakota, and this is the exact answer, the exact split that's given. And I say both C and E are perfectly fine answers. I would suggest, or I would probably answer C, a warm season thunderstorm, just because that's more storm scale. Versus a band of snowfall, that's maybe more mesoscale force, but it depends on the situation. I think both of these answers are good. But the main point of this question was just to make sure that we're kind of on the same page, that I explained the predictability horizon, and I feel that that's a good thing here. So, the first, within that element of pattern recognition skills, using conceptual models, really the launch point for assessing predictabilities is establishing the large scale potential pattern. I think pattern recognition is really that first layer of assessing predictability. And if you think about it, the way that humans think, or the way that humans make decision, is kind of blinking and then thinking. It's the way that we can process information quickly, but still make sure that we're making the best decisions by kind of thinking through those. And I think when we assess predictability, we have to remember how humans make decisions and go through that process in a similar manner. And that's really where pattern recognition skills and conceptual models are, I feel, really, really important within that process of assessing predictability. Each pattern can give you a ton of information as kind of listed on this slide here. So like I said, it's really an important aspect of the modernized forecast process. If you think about how humans make decisions, it's that intuition or pattern recognition. Those snap judgments work astonishingly well, but sometimes they can go terribly awry, and that's where we have to kind of use the blinking part of decision making, or the thinking part of decision making, just to make sure that our intuition is correct at times. Why is that important? Why are conceptual models important? Well, the human, as discussed earlier, can explain the predictability, right? Can understand and explain predictability to our core partners. A machine the NBM or whatever ensemble system you think of, it can tell you that predictability is low or that uncertainty exists, but it's really the human that can understand how subtle differences in the synoptic pattern could affect potential outcomes, and that really helps us to understand predictability. Allows us to build a timeline of decisions in our heads and communicate that to partners. But it doesn't come easy, right? Think about a new forecaster versus an experienced forecaster. An experienced forecaster has a ton of at-bats. They understand, for example, 500 millibar conceptual models astonishingly well, get through that assessing predictability a little bit quicker, right, than maybe a new forecaster can. But I think it's really, really important for new and experienced forecasters to practice these skills every day, right? We need a ton of at-bats in order to really ensure that we're going through the process of assessing predictability in the right way. So, cluster analysis, and we'll get back to cluster analysis later on in this presentation. Hopefully you've all heard of cluster analysis, what it is. We're not going to really go into those nitty-gritty details on this presentation, but I just want to show you how cluster analysis can be used to practice your pattern recognition and conceptual model skills. So for example, here's a cluster analysis. The red boxes are on each cluster. You have cluster 1 in the top left, cluster 2 in the middle, cluster 3 in the top right, and then cluster 4 in the bottom left. Just looking at this, and you can you put in the chat or wherever as well, but think to yourself, which of these clusters would produce the heaviest precipitation across Iowa? Just using your conceptual models of 500 millibar patterns. And I'll give maybe 10 seconds here or so for you to look at this and think about it and pick which cluster, 1, 2, 3, or 4, would produce the heaviest precipitation across Iowa. And then we'll go to the answer. And as you can see in the answer, it's cluster 4 that has the heaviest precip across Iowa. If you go back to the cluster analysis and the 500 and the 4 potential outcomes that result from this cluster analysis, the cluster 4 has the deepest, the strongest trough in the right location to produce the heaviest precipitation for Iowa. Again, using our conceptual pattern recognition, conceptual model recognition skills, practicing that is go to your 500 millibar, think about that, and then click on the precipitation and see if you were correct. You can do that every day and really strengthen your pattern recognition, conceptual model type skills. Here's another example: which cluster would produce the coldest temperatures across kind of that Indiana, Ohio, Kentucky region. I'll leave this up for a few seconds here. And hopefully you pick cluster 3, that top right answer. Obviously cluster 3 kind of had the deepest upper level trough in that right location to produce that had the coldest air mass within that area. So I think assessing predictability, when we think about how humans make decisions, how do we get through this fire hose of data, it's really that thinking, or that blinking and thinking concept, that we can use some sort of pattern recognition skills, and deterministic QPF is one of those ways that we can go through that blinking aspect of how humans make decisions. So I think we can really look for signals within QPF fields. It provides us clues to where to begin our assessment of predictability. It gives us a first guess conceptual model and really points to that intuition of the forcing mechanism that is responsible for that model QPF. And I think that's really, really important, is that we understand that's keeping the science in the forecast process, keeping the science in how we assess predictability for diagnosing the responsible forcing mechanisms for the model QPF. So in these 4 examples here, in the upper left, if we don't kind of look at the dates here, we kind of have higher QPF splattered around the northern plains. To me, that yells convective, that yells storm scale that yells thunderstorms to me. In the upper right, we kind of have a band, a narrower band of heavy QPF. Again, this is just from one deterministic outcome, one deterministic solution, the GFS. But to me, this screams mesoscale, frontogenetical forcing as the main forcing mechanism responsible for this model QPF. Now I'm thinking banded snow. If I go down to the bottom left, I have a large area of light to moderate QPF. To me, that kind of screams Colorado low. And if I go to the bottom right, I have a narrow band again of QPF. It's in the winter. To me, that screams mesoscale frontogenetical type forcing. So using QPF fields kind of as that first guess to lead you down the right path. But remember, blinking can go wrong sometimes, and that's where we have to go do the thinking, make sure that our intuition is correct. This is just a slide that some guidance that we have here at FGF for what to use to diagnose forcing mechanisms. And really the reason that we want to diagnose these forcing mechanisms is that the predictability horizon is shorter as the scale of forcing decreases. It gives us an idea, kind of that first level idea of predictability, of how we should go about messaging this event. And can we be certain, is predictability higher, or is that predictability horizon longer? Can we message more details at longer forecast periods, or maybe it wouldn't be so wise to start messaging those details because the scale of forcing is smaller. So assessing predictability also really needs to include determining if potential outcomes exist, right? Deterministic solutions, ensemble means, probability of exceedance from ensemble systems, they really don't tell you the whole story. And again, that's, I think, where really the human is important in the forecast process, is trying to explain that predictability to our core partners. And really the essence of explaining that explaining why predictability is high or low to our core partners is determining what the potential outcomes are. Really the best way to do this is the 100-member WPC cluster analysis. As a human, you can go through every ensemble member and put them into bins and try to figure out what the potential outcomes are. But really, the cluster analysis does that for us in a much quicker manner, and that's really the purpose of the cluster analysis. When we all get DESI, that has a dynamical cluster analysis as well, and that is really neat too. But really, if you understand your conceptual models, 500 millibar pattern conceptual models, so on and so forth, we can really ascertain what potential outcomes are by looking at this cluster analysis. So just some examples, of using cluster analysis to try to ascertain potential outcomes. In this example, you have the 4 clusters, 1, 2, 3, and 4. There's a couple camps, right? It's not always going to be 4 potential outcomes. If I'm looking at this cluster analysis, there's really just a couple camps. There's 2 potential outcomes that really I'm focusing my attention on. Cluster 1 and 2 are similar, deeper solutions, while cluster 3 and 4 are similar, but they're more progressive, not as deep. And it's really important that, like Patrick said, we're not here to pick a winner. We're not here to rush ourselves to what the most likely outcome is. We're really here to determine what the potential outcomes are, if predictability is high enough to only message one potential outcome. And cluster analysis is a great way to allow to kind of give us that first order guess of what is possible. Here's just another example, different day, but again, this cluster analysis, again, there's really just a couple camps. 1 and 2 are pretty similar, while clusters 3 and 4 are also pretty similar, kind of showing that synoptic pattern of what's possible. Obviously, cluster 3 and 4 are a little bit quicker with that 500 trough, a little bit deeper over the Great Lakes or just north of the Great Lakes area. Again, though, it's not wise to pick a winner. Our partners and probabilistic messaging really implores us to be able to message what's possible, right? But to also tell our partners the predictability for each solution. And the reason we want to do this, I think, is because as humans, when explanations are not forthcoming, poor outcomes ensue. We really, as humans, so think of yourself as a core partner trying to make a decision based on the weather information coming from a National Weather Service office. I really believe that if we explain the predictability, that we provide the reason behind our forecast, provide that context behind our forecast, that better decisions are going to be made. Without explaining the reason why uncertainty or exists or why predictability is lower, forecasts just aren't as useful, and really I don't think as trustworthy. And we have to remember, there's no certainties, there's only outcomes. There's always going to be at least some uncertainty. But if we explain that uncertainty or that predictability, there's going to be better decisions and tend to lead to higher trust. So another element for assessing predictability, obviously, is we want to establish how extreme a scenario would be. And I'm not going to go into too much detail on this, but it is important to understand that we have to establish how extreme a scenario may be. There's a lot of tools available to do this. Again, this presentation isn't really meant to go through training for all these tools, but I just wanted to list these tools as some examples, and I think there's a lot of other great tools out there that we can use to really establish the extremes for each potential scenario that does exist. And like Patrick had mentioned before, if a strong signal, say for a winter weather event, exists on day 6 or 7, even though we don't know the details, I think it's our responsibility to still start messaging in a responsible way, messaging the potential for a higher impact type event. And these tools are good for that as well. So kind of that last element that we want to go over is tying the probabilistic patterns and trends to deterministic conceptual models. I think really, or we really think that deterministic NWP is, and until something better comes along, needs to be the primary tool for employing conceptual models. Ensemble systems, especially if you're looking at the means, tend to wash out the details. Element availability and resolution of deterministic solutions, really, they are needed to apply these foundational conceptual model concepts. And looking at each deterministic solution, if a deterministic solution is close to what we feel is a potential outcome based on the cluster analysis, we can really use that to help us understand a particular solution and to diagnose the forcing mechanisms responsible for the QPF, so on and so forth, to help explain why uncertainty exists or why predictability might be lower. So to finish up here, I just want to look at ways which features in deterministic models can help to explain patterns in the probabilistic data. So one example that actually happened to me last winter season, going through the forecast process, there were two potential outcomes. One, kind of where you have the strongest warm air advection kind of within the thermal axis, and the second where you have the strongest warm air advection kind of ahead of the thermal axis. Potential outcome one, just because of timing of thermal gradients and features or whatever, would probably be mostly liquid, right? The strongest forcing would be where your thermal profile was above freezing, where potential outcome two, kind of the warm air advection is a little bit higher in the atmosphere at 700 compared to 850, and in an area where your thermal profile is mostly below freezing, which would be all snow. Impact-wise, two totally different potential outcomes that probably need to be messaged to our partners. This is what happened, that it was more like potential outcome number 2, where the warm air advection was a little bit higher up in the atmosphere, and it was mostly snow. Again, a little bit of rain on the southern end, but if you're in Grand Forks or Thief River Falls or Bemidji, it was not all liquid, which would have minimal impacts. It was 2-3 inches of snow at rush hour, which increased the impacts dramatically. So yes, I was forecasting this event, and I did not go through all of the elements that I needed to assess predictability. I latched on to a RAP solution that had an area of heavier QPF just ahead of the surface low, more like potential outcome number 1, and really messaged all rain for this event for like Grand Forks and Thief River Falls. Really, I skipped the element for determining potential scenarios. I thought my mindset was too deterministic, and I did not, I did not go down the route of probabilistic thinking. Another way to kind of look at this, what if you're looking at the NBM for this event, and it gives you a couple of different P-type probabilities? That would be a great thing to use, right? The NBM precipitation type probabilities. It probably would have led me down the road of, oh, there's more than one potential scenario that exists. But with that said, the NBM can tell you that uncertainty exists, but ask yourself, can the NBM or any ensemble system explain why that uncertainty exists? And I do not think it can. So again, getting back to deterministic fields and conceptual models, I really think going down to that next step, that next element, they allow us to develop a better message and allow us to pivot toward potential scenarios quicker. And I'll quickly show you a couple examples of each. This first example of using deterministic conceptual models to develop a better message is from, thank you, Phil Schumacher, the suit in Sioux Falls. But basically, let's look at 2 hypothetical cases, case 1 and case 2. They have the same exact probabilities for greater than 1 inch, greater than 6 inches, and greater than 12 inches of snow. With no other information, if we're only looking at probability of exceedance from ensemble members, we'd probably message these the same, right? There's really no way to ascertain how we would message these 2 events differently. But what if I told you case number 1 was a banded snowfall event, strong frontogenesis, so on and so forth, where case number 2 was a warm advection type of an event. The forcing mechanism was more synoptic scale, weaker frontogenesis, more of a shortwave trough moving through the area. So let's look at some individual ensemble members for case number 1. You can, as I scroll through these, notice that each of the ensemble members has a heavy band of snowfall. It's just that each of the ensemble members has that heavy band of snowfall in a different location. And then for looking at the individual ensemble members for case number 2, remember this is more synoptic force. We see that one of the ensemble members has snowfall greater than 12 inches. Some of the ensemble members have 6 inches, some are 6 inches but in a different location, and a few of the other ensemble members are probably weaker with that upper level trough, more progressive and have less snow across the forecast area. So if we look at storm system probabilities, case number 1, somewhere in our forecast area, we're going to get more than a foot of snow. There's a 100% chance every ensemble member has greater than a foot of snow. Or in case number 2, really only one ensemble member had greater than 12 inches of snow, right? So equate that to about a 13% chance somewhere within that affected by the system will get greater than 12 inches of snow. Hopefully you can see that messaging these 2 events should be very different. Think about yourself, an emergency manager or DOT, somebody trying to make a decision based on this forecast information, not knowing the reason why predictability is lower or higher or why uncertainty exists. You may not make as good of a decision until you understand why that uncertainty exists. And that's, I think, where really assessing predictability and having that affect our messaging is really, really important. I think kind of another crazy idea we have is that we can use probability of exceedance fields kind of as a proxy for predictability. So an example from an event we had last winter, we went through our cluster analysis and it indicated two main potential scenarios. One, there's an the upper flow is fast and weak, less snow. Most of the snow further north, where scenario 2, your upper flow is slow and strong. You have a deeper 500 millibar trough, which would lead to more snow, right? And snow maybe even a little bit further south of scenario 1. So, how could we then determine the predictability for each scenario? And, if most of the ensemble members from scenario number 1 have less than 2 inches of snow, and most of the ensemble members from scenario 2 have more than 2 inches of snow, we could use the probability for greater than 2 inches of snow as a proxy for the likelihood of scenario number 2. And this is just an example of NBM 4.1 probability of greater than 2 inches leading up to this event, where we can start really honing in on messaging and turning our attention to scenario number 2. And kind of last example I'll go through is using these conceptual models and proxy probability of exceeding thresholds to pivot toward potential scenarios quicker, right? We can't always say that anything or everything is possible. We have to message what we know. And I think understanding using conceptual models and understanding why uncertainty exists or why predictability is lower or higher, what the potential scenarios are, allows us to pivot quicker toward maybe eliminating a potential outcome. So in this example, we'll use Grand Forks again because that's where I have all my examples from. The snow is crusted over, so in order to get blizzard conditions, given the temperature and the winds that we're expecting, it's going to take heavy snowfall. So we're going to use 0.25 inch precipitation, so probability for greater than a quarter inch of precipitation, kind of as that proxy between heavy snow and light snow, or that proxy between blizzard and advisory type impacts for this particular solution. And you can see cluster 3, what are the potential outcomes? Cluster 3 is stronger further to the northwest with its upper level low, where the other clusters have that upper level low in slightly different areas. Cluster 3 would probably have the heaviest precipitation for our forecast area, where clusters 1, 2, and 4 would likely have lighter snowfall for our forecast area. So leading up to this event, the question to ask is, would you continue to message the potential for blizzard conditions across any portion within that red box or across the Red River Valley? This is the probability for greater than a quarter inch precipitation, the probability for wind to combine with heavier snow that would lead to more widespread whiteout conditions. So in this case, just looking at the probability for greater than a quarter inch of precipitation, I would say there's roughly a 40% chance, especially across the Southern River Valley, for blizzard conditions. But leading up to this event, we see that those probabilities are decreasing. And by the time we get about 6 or 12 hours from this event, the probability has decreased. Has it decreased enough to stop messaging the potential for blizzard conditions? It kind of depends on the situation, but again, just an example of using the probability of exceedance thresholds as a proxy for assessing predictability. So my last slide here, just as kind of a summary of the role of deterministic solutions within the elements of assessing predictability. And the one thing I really want to get across is we have to keep in mind that as we use deterministic solutions, that they're really one of an infinite number of potential outcomes. They have their utility, but we have to keep our mindset probabilistic as we're looking at these. So I will pass it over to Andy, who will kind of go through example of using this in a real-time case from start to finish.
Okay, thanks, Tommy. Yeah, so for a bit of an application, I chosen a rather challenging case. And yeah, I chose one from Central Illinois because there again, that's where I have a lot of data, kind of like Tommy in Grand Forks. So imagine it's a day shift in late January. And yes, this is looking back at a real event. So I realize some of you may end up remembering this, but that's okay. And you're taking a closer look at winter storm potential in about a week from now. So we'll start by checking cluster analysis for potential patterns. This is going to be kind of an end-to-end example. So we're in the first, we'll say we're in the first pillar now. We're looking at understanding patterns and establishing predictability. So when we check our cluster analysis for next week, we see that there's notable ensemble spread regarding interaction between a trough over southern Canada and the upper Midwest and a trough over the southwestern US and their respective depths. Some clusters have a stronger trough, lower height anomalies over the upper Midwest. Some have, like for example, cluster 2, not so much. Same with the height anomalies in the Southwest. Some like cluster 3 and, cluster 4, excuse me, the low height anomalies are kind of focused in the Southwest. When you look at cluster 1 and cluster 4, well, cluster 1, all the cold height anomalies, the low height anomalies are kind of translating across the central part of the US together. There's not so much separation between the two. So we're looking at timing differences here. A lot of factors going on that are going to be at play. So Tommy, go ahead and go to the next slide, please. Regarding predictability horizons, first of all, we recall there can be multiple predictability horizons for the same event, but I'm sure a lot of you saw Randy's chat earlier. There may be different synoptic scale systems that may have different predictability horizons, or multiple synoptic scale systems with similar predictability horizons that are interacting, and that's perhaps going to be an issue here. So a question we could perhaps ask ourselves is, how does the interaction between these two troughs, the one in the southern Canada and the upper Midwest, and the other coming out of the southwestern US, with cluster analysis telling us there's differences in what the height anomalies are going to be and what the time is going to be, how does that interaction impact the overall predictability horizon? I realize that's a bit of a rhetorical question. Well, it's gonna lower. It's gonna with all these different complex interactions, it's gonna make the overall predictability horizon lower. Okay, so quick comment. Next slide, we're gonna look at the deterministic GFS QPF for a week out. And keep in mind, it looks more like the multi-model mean from our cluster analysis than any one cluster, which is kind of curious. I mean, ideally, to do something like this, we'd like it to look like one of the scenarios. But in this case, it happens to look like the multi-model mean. I didn't point it out specifically on the cluster analysis, but if we looked at the ensemble members that were in each cluster, it was really pretty evenly spread. So we had kind of and as far as the raw ensemble members, pretty equal chances of each scenario coming to fruition. So go ahead, Tommy, and go to the next slide. All right, so we can take a look at deterministic model QPF and then start digging into forcing mechanisms, kind of like Tommy was sharing earlier. Yes, this is a deterministic model. So as was discussed, the higher resolution and we being able to discern key features is an important quality of deterministic models, and we need that ability. We need to be able to figure out why some of these things are or may be happening. But keep in mind, this is one possible solution. We have a lot of possibilities coming up here. So On the left-hand side is forecast for Tuesday evening next week. And we see a streak of higher precipitation from central Iowa up into southern Wisconsin. That, if we look, I don't have all the different charts. I don't want to spend too much time here. I know we're getting up close to an hour already, but I know, so we've got, when we look into the 300 millibar charts, we see that there's actually a 300 millibar jet that the nose of that pushes into central Iowa and up into southern Wisconsin during that period. And the left exit region kind of translates close to where that streak of precipitation is appearing. When you look at the higher end precipitation, that area of a 1/4 inch to a 1/2 inch over east central Illinois, there is a shortwave trough that is moving kind of out of the southeast or southwest, excuse me, moves across the area, and differential cyclonic vorticity advection provides some lift ahead of that shortwave trough. And there's kind of a broad area of synoptic scale lift that's responsible for that area. So we're just identifying some of the potential forcing mechanisms that could be responsible for QPF in this case. On the right-hand side, we see the precipitation moving up through the south, up into the mid-south, and then it's catching southeastern, eastern, and southern Illinois a little bit. That's one of the troughs that's moving out of the Four Corners region, and then it heads out into the Midwest. In this particular run, it was taking kind of a trajectory toward central Illinois, and this particular run, it was looking like that would be mostly rain, but as you saw in the cluster analysis, we have quite a few possibilities here. Go ahead and go to the next slide, please, Tommy. So from the deterministic model, from this deterministic GFS run even, we can see that the QPF appears in 2 separate time periods. The first time period comes just after the cold air associated with that Canadian upper Midwest trough arrives. And the second, in this particular case, is associated with lift ahead of that trough moving out of a shortwave trough moving out of the southwestern US. That's from the deterministic model, identifying the forcing mechanisms. Well, going back to the clusters, we can see that these 2 time periods have a variable amount of separation between them, and we can there's lots of possibilities here, and the spread in the depth of each trough is high, and so details in thermal fields will ultimately determine precipitation type. It's tough to nail that down at this point. Go ahead and go to the next slide, please, Tommy. All right, so the next pillar, the next element, we are wanting to establish what are our potential extremes of our scenario. And there we're diving into some of the machine learning and multi-model ensemble-based tools. One tool we can look at is the EFI, the ECMWF Extreme Forecast Index. In this particular case, we've got plots for QPF and for snowfall. From the QPF plot on the lower left there, we see that confidence is growing in a climatologically unusual QPF event from southeastern Missouri into central and southern Illinois and up into Indiana and Michigan. That area that's the 0.5 to 0.6 EFI. So that's in a statistical sense, what that's saying is that the forecast, the curve that represents the forecast ensemble is sufficiently far enough away from the climatological ensemble QPF curve that we're generating the EFI value of 0.5 to 0.6. Then we talk about shift of tails, and where that shift of tails value is greater than 0, where that 0 contour shows up. At least 10% of the ensemble is forecasting an extreme event, which extreme is defined as above the 99th climatological percentile. And we see those areas of shift of tails greater than 0 are appearing for both QPF, a fairly large area, and we're even seeing it appear for snowfall. So high-end snowfall event is a possibility. Go ahead and go to the next slide, please, Tommy. Okay, another thing we can look at is threshold probabilities for QPF, snowfall or ice accumulation from, and these particular plots are from NVM version 4.1. These are pretty high-end extremes, the ones I happen to have. So these example plots on the lower left, they show the probability of greater than 12 inches of snow over a 48-hour period that's centered around the time period we're looking at. And mostly zeros over central Illinois, but we do see some lower single-digit numbers showing up just to the northwest. So they're over Missouri and up into Iowa, northern Illinois, southern Wisconsin. So we do have at least some single-digit probabilities of greater than a foot of snow showing up. On the right-hand side is 48-hour probability of ice greater than a quarter inch. Some low single-digit probabilities over central Illinois, but again, the higher end values are to the northwest, kind of similar location to where the higher snow values were. And go ahead and go to the next slide. So yeah, here's a reminder of what that pillar is, mainly just because I could fit it on this slide, didn't fit it on the other. So non-zero probabilities of both a foot of snow and greater than a quarter inch of ice accumulation are over or near central Illinois, but the highest probabilities for right now of both of those are to the northwest. And for right now, the probability of ice accumulation of greater than a quarter inch is slightly greater than the probability of a foot of snow for right now at this snapshot in time. Okay, go ahead and go to the next slide. So now we're on to the third pillar, the third element, where we've looked at our cluster analysis, we've looked at deterministic models and gotten conceptual models together, and we've looked at some of the probabilistic tools. Now we want to tie them together. The strength and the timing of the northern trough, that upper Midwest trough in this case, and the track of the shortwave troughs coming from the southwestern US, from that the low height anomaly down there, it could conceptually make a big difference in precipitation type and the location of heaviest precipitation. So this is one of those cases where we've got predictability is fairly low. It's not like we've got one well-defined trough and it's just a matter of timing it and exactly where it's going to be. It's not as clear-cut, unfortunately, but we can use cluster analysis to know that. Conceptually, if a deep northern trough were to arrive earlier, then perhaps plenty of cold air may be in place ahead of the arrival of any shortwave troughs that are coming from that low over the southwestern United States. Okay, next slide. All right, so based on our examination of deterministic and probabilistic data, we can fairly reasonably say confidence in an impactful precipitation event somewhere in the Midwest is high. And if we go back to the EFI, for now, that stretch from central southern Illinois up into Indiana and Michigan is the highest probabilities for the higher end QPF. But given the multiple troughs and the associated forcing mechanisms that are all interacting with thermal fields, when we start talking about the location, precise location of heaviest QPF, as well as start talking about boundaries between precipitation type changes, that's getting pretty low on the predictability scale for now. However, we do know that the potential exists for either a high-end snow or ice event. Those are both in play, or perhaps they both happen in this case. All right, next slide. So as far as what happened, on the left is verification of the heights at 0Z Thursday, February 3rd, and that's the event was from this past winter. So it ended up that the trough coming from southern Canada, the upper Midwest, and the height anomalies over the southwest were both quite low, and the trough in the Midwest showed up early enough that we had plenty of cold air present over most of the Midwest. We look at the observed snowfall on the right from eastern Missouri through central and northeastern Illinois up into Indiana. Lots of 7 to 10, 11 inch snowfall reports. Even we did show up with a 12 at Springfield there. And 4 to 7 inches down south of I-70, and which is a pretty notable event for the folks down there. Okay, next slide, please. So as far as what happened, cold air pushed through central Illinois on Tuesday during the day, so ahead of any precipitation. And then I recall the multiple shortwave troughs that we were observing in the deterministic data. There was a shortwave trough lifted north along the front on Tuesday night into Wednesday morning, and there was an upper jet coupled with that and resulted in several inches of snow with that, and that was mainly along and north of I-72 going through our area. So that was mainly the northern part of our region here. And there were ice accumulations from about 1/10 to 3/10 of an inch in the southern part of our CWA. Ice accumulations greater than that down toward the Ohio River down in far southern Illinois. Second trough moved out of the Four Corners region that was emanating from that low height anomaly in the southwest late Wednesday night. And it took a pretty southern track, pretty southern trajectory, another round of snow into Thursday. And so even our areas in our southern CWA switched to snow by mid-morning Thursday, and we picked up that 4 to 7 inches. Okay, next slide, please, Tommy. So that was our kind of our end-to-end scenario. A couple of things to talk about before we close out. As far as, and we've mentioned this a couple times, should we assess predictability in any certain order? On the right there is a suggested methodology from a talk that Chad Cravell gave at the NWA meeting in 2020 that has some suggested steps to take. And I know I've even incorporated this into my forecast process several times. But when you look at the steps, they bear quite a bit of similarity to the elements and pillars that we've discussed in this talk, just perhaps maybe in a little bit different order. See what works. I mean, the order you go through the pillars within this process may not matter so much. See what works for you, but what does matter is that you use the pillars, that use all the pillars, that you're taking into account conceptual models, that you're looking at the deterministic data for forcing mechanisms, and also comparing that to ensemble distributions, to cluster analysis, looking at the probabilistic data and machine learning, and then from your conceptual models, you're able to explain why does the probabilistic data look like it does. And so, yeah, what matters is that you use all the pillars. Go ahead and go to the next slide, Tommy. One more concept as far as making forecast decisions. Encourage you to involve everyone that's in the forecast process, and when we're assessing predictability as much as possible. Make sure to get everybody's point of view, get everybody's take. When we all work together, each of us perhaps sees something that the others don't. And so taking the wisdom of the crowds, thinking about super teams, thinking about from a super forecasting perspective, we're going to be stronger when we're all taking what each of us are seeing together, rather than perhaps going with what the strongest voice says or what the first person says. And then I kind of all dive in with that, and we fall into groupthink sometimes, that little cartoon in the corner where the man at the front saying, all those in favor say aye, and everybody's agreeing, aye, but everybody's doubting in their head and secretly, say it ain't so, oh, no way, you gotta be kidding. So if you have a different perspective, speak up, and we can all give our perspective, we can all work together and ultimately do better for our partners. Okay, next slide. Thanks, Tommy. And so this just decided to put the elements up one more time to close, just so you could look at them one more time and have this up while we're wrapping things up. And just wanted to mention here in closing that this PowerPoint, we're not planning this to be the end and like, okay, we did this presentation and okay, you got it all and you completely understand assessing predictability. We want there to be more opportunities to practice this process. It's important that we all do that. And so date is to be announced, but look for a scenario to come out down the road when you will be able to take that scenario and get some hands-on practice with this process. And so, yeah, we really want to be able to do that. So, yeah, sometime down the road, you'll be able to have another chance to get your hands on some data and practice this process for yourself in a hands-on way. And I think that's all we have. And so, Jessica, I'll turn it over to you and we can take any questions.